So I think we can start. It's a great pleasure to have for our today JAC Marta Burgay. Marta graduated and got her PhD in astronomy here at the University of Bologna, working with D'Amico and the docente Roberto Fazio. Since 2004, she's a researcher now, short researcher at INAF-Cagliari. And then she has been always involved in investigation of neutron stars, in particular in the analysis of pulsars in radio band. Thanks to the discovery and the analysis during her PhD of the first and up so far the only system of double pulsars, she received various prizes, including the Galactic Prize in 2006, in 2005, in 2006 the Young Researcher Prize of International Union of Applied and Pure Physics. In 2014, she was named Chevalier de l'Autonomie by the Valle d'Aosta region where she comes from. And in 2015, she was named the Sardinian Woman of the Year. Today, she will talk about pulsars with Marta. So thank you, Marta, and let's start.
Thank you. Thank you, Bettina. Thank you for inviting me here. Thank you for pronouncing my name right. We come from the same place, so at least there is this advantage. And I think she and a few others, including Roberto Fazio, remember how to pronounce my surname. So yes, as Bettina told you, I'm going to talk about pulsars with MeerKAT, and in particular, I will show you some of the first results, just like a couple of highlights from the MeerTime and TRAPUM large survey projects that have been ongoing at MeerKAT in the last 3-4 years. So since I know that at least there should be also some PhD students here in the audience, I have split my talk in like 2 parts. The first is more generic and deals with the basics of what pulsars are, even though as everyone knows in the audience, but just to be on the same space. And I will briefly describe also the method that we use to exploit the clock-like nature of pulsars to do many experiments, which is the pulsar timing method. I will very briefly describe the MeerKAT telescope, and then I will describe the 2 experiments that I want to talk about: the MeerTime, which deals with studying known pulsars with very high details, and the TRAPUM, which deals with searching for new pulsars with MeerKAT. And as I was mentioning, I will present you just a couple of highlights on the discoveries. And if I have time, I will show you like a global set of results and some future perspectives. Okay, so let's start with pulsars. As you know, pulsars are highly magnetized, fast-spinning neutron stars that emit beams of radio waves, as you can see in the little animation there, from their magnetic poles. If the geometry is favorable, we can see with our radio telescope 1 flash of radio waves for each pulsation, rotation of the pulsar. So we can measure the spin period of our pulsar very precisely. Very quickly, how do pulsars work? The radio emission of pulsars is powered by the rotation of the dipolar magnetic field. So we can write the energy of the pulsar through basically the Larmor formula that we can write also in terms of the magnetic field, BS, there, and spin period of the pulsar. And the energy is emitted at the expense of the rotational energy of the neutron star. So we can write also the kinetic energy of the pulsar, again, depending on the pulsar spin and pulsar spin derivative, since the energy is emitted at the expenses of the kinetic energy. The pulsar is slowing down with time, as we will see better in a second. And by equating those 2, we can also get some information, information about the surface magnetic field, assuming that it is a dipolar magnetic field that depends on spin period and spin period derivative, and also by integration, I guess, on the age, the so-called characteristic age of radio pulsars. So since we can measure both the spin and the spin down rate of radio pulsars by observing them in time, we can use these 2 parameters two plots, a sort of pulsar evolutionary diagram in which on the x-axis, I'm using the mouse here so also people online can see, we have the spin period, on the y-axis the spin period derivative, and the diagonal lines are equal magnetic field lines and equal age lines. And well, a pulsar, a neutron star, is born with fast rotation and high magnetic field because it's the result of a core collapse supernova in which angular momentum and magnetic flux are conserved during the collapse of the core of the star. So it rotates fast, tens of times in a second, more or less, and with high magnetic field of the order of 10 to the 12, 10 to the 13 Gauss. As time goes on, the pulsar slows down, crossing this PP dot diagram in this way, with maybe the magnetic fields also decaying, until it crosses that purple line that you see in the diagram, which is labeled death line, for values of the spin period and magnetic field below, which basically the pulsar emission mechanism is not efficient anymore, and the pulsar dies, basically. That would be the end of it, unless the pulsar is in a binary system. And at that part, which point the companion star in the little animation there, it's a low mass binary that starts pouring matter through mass loss through its Roche-Loeb overflow, and through through an accretion disk, it can start transferring matter, and with it also angular momentum on top of the neutron star that, as you can see in this little animation, is re-accelerated by this mass and angular momentum transfer. In this phase, the pulsar is seen as an X-ray binary, either a low mass or a high mass, depending on the companion star. And depending on the companion star, it can be re-accelerated to periods of tens of milliseconds, or if it has a low mass companion, to milliseconds period. The magnetic field also decays, and we don't exactly know yet how, but it's probably linked to the accretion phase itself. And so when the accretion stops, when the X-ray emission stops, if the pulsar is again above the death line, it can shine again in radio waves as a millisecond pulsar. So a pulsar that's rotating hundreds of times in a second, up to the fastest that we know of, rotates more than 700 times in a second, and with low magnetic fields and low spin down rates. For this reason, pulsars, well, actually pulsars in general, but in particular, these fastest rotating millisecond pulsar are extremely stable rotators. You can imagine a ball of 1.5 times the mass of the sun packed in 20 kilometers that rotates 700 times in a second. It's impossible to go there and change its rotational rate. So it's a very, very stable clocks, and the faster millisecond pulsar even more so. And for these reasons, they can be used as clocks in space, as test beds for many different studies in physics and in astrophysics in general. So in this slide, I'm summarizing a few things that we can do with pulsars. The first thing that we can do is of course, try and study its emission physics by looking at the radio beams, but also at gamma ray on optical emission from the most powerful pulsars that we know of. And so try to understand how they actually work, which is kind of still a mystery, especially in the radio band. We can use the beams and the radio beams of the pulsars as probes of the interstellar medium, both of the electronic content of the interstellar medium by looking at how the interstellar medium breaks, basically slows down at different frequency the emission of our precisely timed radio pulses, and also to study magnetic fields, since the radio emission of pulsars is polarized. So we can study the rotation measure of pulsars and have information about the galactic magnetic field along the line of sight. Again, by studying in detail the pulsar emission and its polarization, we can also get information about these extreme magnetic fields, which are the most extreme that we know of. Since the fastest rotating millisecond pulsar are almost always in binary system, we can use their precise sticking to study the binary itself and to study binary stellar evolution by consequence. And maybe most interestingly, and I will show you something about this in more details later on. We can use the clock-like nature of pulsars to study gravity. We can basically follow how they tick and see how this precise clock fall in the curved space-time, which can be curved either by the companion star in a binary system, or by a passing gravitational wave. And these kind of distortion of the space-time have an impact on the times of arrival, as I will show you, of pulsars, of pulsar ticks. And so we can use them to study gravity with very high details. We can use them, of course, since they come from supernova explosions, to have information on how supernova explosion works. For instance, by looking at how pulsars move in space, measuring their proper motion, and by measuring masses and spins, and in some cases, in some very peculiar cases, also moment of inertia of neutron stars, we can use them to study equations of state of superdense matter. So many, many things we can do with pulsars, and most of which can be done thanks to, as I was mentioning, their clock-like nature. The way in which we exploit this characteristic of radio pulsar to do all these studies is the so-called pulsar timing method, which on paper is relatively simple. We have, when we discover a pulsar, we can write a little set of ephemeris, of parameters for it. We know more or less its position in the sky, which is not very accurate. It has the accuracy of our radio beam, so few arc seconds. We know its spin period, and maybe we know something about its orbital characteristics from the first few observations. So on the basis of this model that we can write, we can predict times of arrival of all of the pulsars from the given pulsar, and then we can go and measure times of arrival from real observation that we do with different cadences. We can observe a pulsar every week or every month, depending on the precision that we have and the kind of science that we want to do. We create a timing residual, so-called timing residual, by basically subtracting predicted times of arrival from measured times of arrival. And if the model were perfect, these timing residuals across different observations would be basically flat or randomly distributed around the zero with a small root mean square. If we have an error in one or more of the pulsar parameters that we plugged in the model, this would reflect in specific trends in our timing residual. So by fitting these trends out, we can recover very precisely the various parameters of the pulsar. I have here like a super basic example that shows you how this works in practice. The red arrows are 3 measured times of arrival from 3 different observations. The blue arrow is the spin period in our model. And as you can see here, there is clearly a discrepancy. The spin period is clearly underestimated. So there is a deviation between predicted and observed time of arrival, which in this case increases linearly with time. So these are our timing residuals across time for 3 observations. And by fitting a linear trend out from the timing residuals, we can precisely measure the spin period of the pulsar. If we do that for long enough, we can reach precisions in the measurement of these parameters with very high, with a very high number of decimal digits. I will show you an example a little later on. So a linear trend in our residuals means that we have to correct the spin period in our model. A parabolic trend means that we are not accounting correctly for the spin period derivative. To measure it, we have to observe the pulsar for a few months. Otherwise, the parabolic trend might be confused with a linear trend. Something like this is a trend like this in timing residuals means that we are measuring that in our model, the position of the pulsar is wrong. These are the top plot there shows you timing residuals with a sinusoidal variation with a period of a year, which clearly tells us that the problem is that we are not accounting correctly for the fact that the Earth is rotating around the sun, or better yet, the solar system barycenter. So if the position of our pulsars, when translating the times of arrival as we record them at the telescope, which is of course not an inertial reference frame, to the inertial reference frame of the solar system barycenter. If the position is not correct, this will introduce this kind of timing residuals. So by fitting this out, we can also very precisely measure the position of our pulsars, even though our angular resolution is still tens of arc seconds, we can reach sub-milli-arc second precision with this method. We need years, at least a year, basically, to do this trick, though, observing the pulsar every month or so. And in the bottom plot here, you see the similar effect, but we think with the increasing amplitude. And this is the effect that we have in our timing residuals if the model does not take into account the pulsar proper motion. So basically here, the position of the pulsar is changing with time. So the effect of the correction of the solar system barycenter gives this effect. And to measure pulsar proper motion, we need a few years of observations in pulsar timing. Same thing we can do, same thing that we've done with the pulsar Earth system, we can do with the pulsar companion system if we find the pulsar in binary, and by again transforming the times of arrival from the pulsar-centric reference frame to the barycentric reference frame, we can also, and fitting out the little effects in the timing residuals, we can also measure the 5 Keplerian parameters of the orbit, orbital period, projected semi-major axis, eccentricity, omega is the angle of periastron, and T0 the time of periastron. And while combining them basically with the Kepler third law, we can also get the mass function. So in the second term here, we have all parameters that are measured through timing. And here we have mass of the companion, mass of the pulsar, and inclination, plugging a normal reference mass of the pulsar in here, which is usually like 1.35 or 1.4 solar masses. We can get an estimate for a lower limit for the companion mass, just out of measuring times of arrival over repeated observations and doing this trick. So if we do this correctly, we should end up with something like this. So as I was mentioning before, across time, these are the timing residuals, and they are scattered around the zero, randomly distributed with a small RMS. So this means that the model is describing correctly our observations, and we can get this kind of precision in the timing, in the parameters of the pulsars that we are observing. As you see there, right ascension and declination are known with something like micro-arc-second, tenths of micro-arc-second positions. The spin period is known at the 18th decimal place, which means that if we want to predict the time of arrival of any given pulse of this one pulsar a year from now, we can be sure, unless something happens to the pulsar or between us and the pulsar, that we will get it right within a few tenths of nanoseconds, right? So this is how precise these clocks are. And as you can see, we have also measured proper motion and orbital parameters with quite high accuracy. In some cases, though, even after fitting for all of these parameters, we still remain with some trends in our timing residuals, which means that we need to plug in more equations, more parameters, and we can exploit the timing method to basically study additional physics. In particular, what we are interested in, and one of the things that we are studying, as I will show you later with MeerKAT, is the possibility to test relativistic gravity with pulsars. This can be done very effectively in this post-Keplerian formalism, in which not only we fit out Keplerian parameters of the orbit, but also these so-called post-Keplerian parameters, which for general relativity are basically these 5. Omega dot is the periastron advance, so the fact that the orbit is not a fixed ellipse, but it's moving. Then we have R and S, the range and the shape of the Shapiro delay, which takes into account the fact that, well, the companion is curving the spacetime, so we have some extra delay, and the rate depends on the mass of the companion, and the shape depends on the inclination of the orbit. So the more massive and more edge on the orbit is, the better. Then we have gamma, which is parameters related to gravitational redshift and time dilation, and the orbital decay, so the shrinkage of the orbit due to the fact that in GR, we predict that the system is losing energy through the emission of gravitational waves. So we can fit out these 5 parameters, extra parameters from our timing residuals and interpret them not necessarily as in the framework of GR. For every theory of gravity, we can write a set of 5 equations, one for each of these parameters, which in every theory of gravity will be slightly different, but in every case, they will depend on the Keplerian parameters of orbit, which we know very, very precisely from pulsar timing, and on the mass of the pulsar and of the companion. So we can write up to 5 equations with only 2 unknowns. So of course, by measuring through pulsar timing only 2 post-Keplerian parameters, we can get separately the masses of the pulsar and of the companion, which has interesting consequences in the study of neutron stars and neutron stars equation of state. But also, if we measure any of the other 3, we can compare, well, we can plug in here the masses of the pulsar and the companion. Capital M is the sum of the 2. And so get a prediction for these parameters. And if we measure one or more of the other parameters, we can get a test of GR. Again, only by measuring times of arrival and doing this timing trick, which is the basic of all of that science that I was showing you before. So pulsars are quite faint objects. And in fact, we know all of the pulsars that we know of, which are more or less 3,000, are found, except for 30 or so, in our own galaxy. 30 or so are found in the Magellanic Clouds. And for this reason, the most used and successful telescope that have been used until recent, well, still, but in the years for the southern hemisphere are the Parkes radio telescope, 64-meter diameter, located in Australia, which is responsible for finding something like 1/3 of all of the pulsars that we know of. So it's a very, very successful instrument for pulsar science. And for the northern hemisphere, the Green Bank telescope, 100-meter antenna located in West Virginia in the US, which also has a very high record of pulsar discoveries, in particular in globular clusters. But, well, 5 years ago, a new instrument changed a little bit the panorama of pulsar science, of science in general. Just last week, there was a conference about the first 5 years of science with MeerKAT. I wasn't there, but I've been told that it was very, very interesting. Many results in pulsar science, but of course not only. So MeerKAT is an array of telescopes, 64 antennas with a 13.5-meter diameter located in South Africa. It has a very low system temperature and a very high gain and very large observing bands, which makes it like something like 4 times as sensitive as the Parkes radio telescope, at least, depending on the instrument that you use, on the receiver that you use at Parkes, and almost twice as sensitive as the GBT. So this has an incredibly high impact on all of the science, and well, for us, of course, also in pulsar science. Given its characteristic and given how it is very suitable for pulsars, 2 of the large survey projects in pulsar science in a large survey project with MeerKAT deal with pulsars. One is TRAPUM, transients and pulsars with MeerKAT, with, as I was mentioning at the beginning, deals with searching for new pulsars. And we have like 4 sub-projects on pulsars and a 5th that uses the data from all of the other projects to search also for fast transient. We have these 4 different surveys, depending on the kind of target that we want to search pulsars in. The first quite obvious target are supernova remnant or pulsar wind nebulae, in which we know that should host a neutron star. So we point at these targets to search for new pulsars. Another targets are Fermi unidentified sources. I will talk a little more about this in a little while, which are very interesting. I mean, Fermi has a very large catalog of unidentified sources. Some of them, many of them, are point sources with the spectral properties that resemble pulsars. And so looking at these sources is a very good way to find new pulsars, and especially the most energetic young and millisecond pulsars. Third target are globular clusters. Again, I'm going to say something more about these, but in general, we expect to find many neutron star, many recycled millisecond pulsars in these old stellar system, old and dense stellar systems. And there is a fourth topic which deals with searching for new pulsars in also nearby galaxies, because as I was mentioning before, most of pulsars that we know of are found in our own galaxy. And so having population in other galaxies with other characteristics can help us in trying to understand how the neutron star population changes in different types of galaxies. The other project is the MeerTime project that deals with timing follow-up observations of known pulsars. And again, this is split in 4 subtopics. One dealing with the study of relativistic binary pulsars and in general binary pulsars, which is why I was focusing a little bit on that specific point for pulsar timing, because it has a relevance. Here, there is a second point, in a second project in the MeerTime project that deals with using pulsars to detect gravitational waves. I think you had here a talk about this topic last week or 2 weeks ago. But the basic idea is that since we have these very precise clocks, if we want to detect a gravitational wave of a long period as those emitted by supermassive black hole binaries, we can use an array of pulsar to search for little discrepancies that this kind of long period gravitational wave would impact on the various pulsars. And we use many pulsars to find a sort of quadrupolar relation between the little difference in the times of arrival from not just one pulsar, but from many, so that we are sure that the signature that we are finding comes from gravitational waves and not from something else. Third project is to observe, again, as in the TRAPUM project, to observe pulsars in globular clusters, known pulsars in this case. And this has a relevance not only because we expect to find many millisecond pulsars in globular cluster, and so to be able to do all of the other science with pulsars in globular clusters, but also because we can use pulsars in globular clusters to study the globular clusters themselves, to study the possible presence of non-luminous matter, maybe even intermediate mass black holes at the centers of the cluster, by studying how the pulsar moves, the various pulsar move within the globular cluster, or also to study the intracluster medium, its electronic content and its magnetic fields. And the last project that we are carrying out within the MeerTime LSP is the so-called 1000 pulsar array. This is the only project that does not deal with the millisecond pulsars, so that does not explicitly exploit the timing capability, the clock-like nature of pulsar, but studies many pulsars to have more an idea on the pulsar population that uses these pulsars to study interstellar medium and emission mechanism from pulsars. Here we have like the pulse profiles for 4 very weird pulsars that have very strange effect that have to do both with the pulsar emission mechanism and with the interaction of the radio signals with the interstellar medium. So has been a very fruitful project. So as far as INAF, and in particular the Cagliari Observatory where I come from, is concerned, these are in blue and cyan the project in which we have involvement, and in particular the blue ones are chaired by one of us at the Cagliari Observatory. So we have 3 of the sub-project followed up by us. Chaired by us. I'm in charge of following up all of the discoveries from the TRAPUM search project. So I think in INAF we have in a very good position to exploit this extremely good data set. And I'm going to now describe some of the results, in particular from the Fermi and globular cluster sources, and in which we are more involved than in others. And if I have time, I will show you some other things in a more schematic way. So why looking at Fermi sources to find more pulsars? But well, you can see here in the graphic on the left, there is the number of discovered galactic millisecond pulsar across year. In 2008, I think, Fermi was launched. And as you can see, almost a quarter of all of the millisecond pulsar in the galactic field have been found by targeting Fermi sources. So basically, Fermi unidentified point sources are a treasure map to find new extremely precise clocks, the new extremely precise clocks that millisecond pulsars are. And in the plot on the right, you see a subset of these pulsars, which are called spider pulsars. I have a slide on them. The next slide describes what they are. And as you can see, more than 2/3 of these kind of very strange, peculiar pulsars have been found through by targeting Fermi sources. So again, this is a treasure trove for very peculiar and interesting objects. So these spider pulsars, they are called spiders because they are divided into subcategories that have spider names, the black widows and the redbacks. Redbacks are the same basically as the black widows, but it's the Australian version. Black widows have very small companion masses. And this is probably because, well, what we think is because the star, the companion star, matter is being ablated by the pulsar emission power. So basically, the pulsar is eating its companion star, which is why it's called black widow. And the matter that it's stripped from the companion star is responsible for eclipsing for like 10% of the orbital phase, the radio signal. The redbacks have non-degenerate, more massive companion star, 0.1, 0.2 or more companion stars, which probably are still pouring matter from their Roche lobe through Roche lobe overflow, but the matter is not accreted on top of the neutron star, so it's not shining as an X-ray pulsar because the radiation pressure of the radio pulsar is keeping the matter away. And in this case, we have eclipses lasting for even more than 50% of the orbit, which is why this kind of pulsar are very difficult to find in a completely blind search. While by pointing at Fermi sources, we know that these host many of these systems, and so we can observe them more than one time and at some point be able to find this kind of very interesting system. These systems are interesting for many reasons. We can study accretion physics through them. We can study plasma physics by looking at how the matter surrounding the system impacts and absorbs the radio signal from the pulsar. We can study binary evolution, redbacks. Among redbacks, we have like 3 pulsars, or 4 maybe now, I don't remember, that have shown transition between a radio pulsar state and an accretion phase. So we can see X-ray emission every now and then when the matter manages to reach the neutron star surface and switches off the radio emission. So we can study even binary evolution, accretion physics. And since the companion stars are relatively bright, usually we can do also optical studies and do some fitting of the light curves. And by putting together the information from the optical and from the radio, we can get information on the masses of both the neutron star and the companion star in the system, and have some also information on the pulsars equations, on the neutron star equation of state. So this is a little summary of what we found in this project so far. By targeting something like 100 and something point sources in Fermi, we have so far found 33 new millisecond pulsars, plus 7 other long period pulsars, probably not related to Fermi. This is like 1/4 of all of the Fermi, of all of the pulsars that were found targeting in the years Fermi unidentified pulsars, proving that MeerKAT is very successful in this matter in just like 3-4 years. 31 are in binary systems. In 2 of them, which we haven't timed, we had followed up for a year or so still, so we don't have a long enough baseline for now. But we do see potential for measuring these relativistic post-Keplerian parameters, and so for measuring very precisely the masses within those systems. We have 1/3 of all of the pulsars that we found are spider pulsars, which is kind of impressive and kind of annoying because they are harder to follow up. But on the other hand, we were able to do optical studies, at least so far for 6 of them, and get mass estimates out of them. Interestingly, when you do this kind of trick of searching for radio pulsation in gamma ray point sources, what you end up is having the timing ephemeris, so the rotational, orbital, and positional characteristic of your pulsars, with which you can go back to the gamma rays and find also gamma ray pulsations, which is very hard to do in a blind way, because I mean we get one gamma ray photos every now and then, and so searching for a periodic and modulated signal directly in the gamma rays is very, very hard. But once we do that, once we are able to find gamma ray pulsations, all of a sudden we have like 15 years of data, right? So these are in the vertical axis, there's the time, and the second plot shows the orbital phase. And the red points are our radio data, which are blown up. These are the timing residuals in time and orbital and day of the year for our pulsars. So we first did the little game of fitting out the timing, the various trends in the radio timing residuals, then use the results to refine our solution by searching gamma ray pulsations. And in the work that we are about to publish about these studies, we also have developed a new method to jointly time the times of arrival from the radio and the gamma ray photons, which allows us, well, first of all, to minimize the use of radio telescope time. As soon as we have a precise enough set of ephemeris to find gamma ray pulsation, we can drop the radio, which is hard to obtain, it's very oversubscribed, and keep on doing our timing with the gamma rays. We have 15 years of data, so we can have precisely the spin down rate and the position of the pulsar without the need to observe for more than a year, and also the proper motion, while at the same time keep, thanks to the radio data, the high precision that the radio timing allows us to reach. So it's a sort of like win-win situation that we can have thanks to this joint timing. So moving on to the next sub-project, which is common to both large survey projects that we are working with at MeerKAT. We want to search and study pulsars in globular clusters. While globular cluster, well, I said it a little bit already, globular clusters are old structures, so we can create the old and recycled millisecond pulsars within these clusters easily, even more so because of their high stellar density that allow for formation and also disruption actually of binary pulsars, so enhancing the probability of having a neutron star within a binary system, and so to recycle it to a millisecond pulsar. And in fact, about 50% of all of the known pulsars, the known millisecond pulsars, are found in globular clusters. So half are in globular clusters in very small spaces, and half in the whole galaxy. And moreover, since also disruptions of binary and stellar encounter and exchange of companions is favored in these dense systems, we can create very exotic millisecond pulsars because they can encounter a different companion with respect to the one that have reaccelerated them and acquire eccentricity, which makes easier to measure those post-Keplerian parameters that I was showing you before, and also form really exotic systems in which, for instance, we hope to find millisecond pulsars with other millisecond pulsar companions, millisecond pulsars with maybe black holes, and all sorts of weird things that in the galactic disk would not be possible through stellar evolution alone. So thanks to these stellar exchanges. So globular clusters are super interesting. That is why we have been targeting with TRAPUM, with TRAPUM 28 of them, with the aim of like doubling the the pulsar population within globular clusters, also to increase the population, to increase the number of globular clusters with known to host pulsars. We know now 40, I think, or so globular clusters in which we know at least one pulsar. And the reason why in some clusters we find many pulsars, in some others we do not, it was partly clear. It depends on how dense they are, if they are core collapsed or not, but it's not as clear as one would think. So by searching for pulsars in more globular clusters, we might have a better idea of how this works. And of course, the aim is also to find extreme and interesting pulsars in these systems. The TRAPUM survey has been really successful. We know now before MeerKAT and also the fast radio telescope in China entered the game, we knew of about 150 millisecond pulsars in globular clusters, and in only like 4 years of observation, we have now 90 more, and including fast, we have already doubled the globular cluster, the pulsar globular cluster populations. This is the summary of all the discoveries that we've done so far. They are actually 94, including this last 4 from GLIMPSE CO1 that a student of mine has just found. And as you can see in the notes there are very different kinds of systems, eclipsing binaries, extremely eccentric, so probably coming from a stellar encounter, very massive star, a couple of pulsars with companions that have masses compatible with them being like planets or planet-like bodies, and very different sorts of interesting things. One of the most successful searches that we've carried out is that on NGC 1851. We knew of just one pulsar in this cluster before, and we have now 14 new pulsars discovered in this cluster. It was very interesting and fruitful to observe this cluster. The paper has been published by my colleague at the Cagliari Observatory, Alessandro Ridolfi, a couple of years ago. And among these, the jewel of the crown is this NGC 1851E, so the 5th pulsar that we found in the system. On the left, there is a discovery plot. On top, you have like the pulse profile. The gray plot here shows how the pulse is changing across time, and here across frequency. And on the right-hand side, we see basically, this is not timing residuals. On the x-axis, sorry, on the y-axis, we have the observed spin period. So this is basically a rotation curve for our pulsars, which we can fit for the orbit. And as you can see, the fit that we've done, it's very asymmetric, meaning that this pulsar is in a very eccentric system. These are the parameters that we were able to find just through this analysis of how the Doppler effect basically is changing the observed speed period. And as you can see, the eccentricity is very high, 0.71. And the other pulsar parameters, if you plug them in the mass function equation, tells us that the companion mass, if we use, for instance, a typical pulsar mass of 1.4 solar masses, must be larger than 1.5 solar masses. So it's a kind of very interesting range for a companion of a pulsar. Usually we have pulsars with white dwarf companions, maybe a heavy white dwarf, but usually below 1 solar mass. So this is quite interesting already. Joining the MeerKAT data to some archival GBT data, we had like 6 extra detection with GBT from previous years. We were able also to measure one of those post-Keplerian parameters of the orbit, the advance of periastron, omega dot, which is directly proportional to the total mass in the system. So by measuring these extra parameters through proper pulsar timing, as I showed you before, we can get total mass of the system of 3.9 solar masses. This is 1 solar mass larger than any other binary pulsars that we found so far. So this is already a quite interesting result. Putting together the results from the omega dot and the mass function result, we can already say that the companion mass must be higher than 1.84 solar masses, but we can do even more because we are not detecting yet other post-Keplerian parameters, so we cannot get directly a measurement of the two masses separately, but we can put some constraint from the fact that we do not, with our current precision, measure, for instance, the Shapiro delay, the effects of the Shapiro delay, which, as I was mentioning to you before, are related to the total, to the mass of the companion and to the orbital inclination. So because we are not measuring these effects, we can put extra constraints on the mass of the companion and on the inclination. And this gives us this range for the mass of the companion from 2.1 to 2.7 solar. So, well, one could think, well, maybe there is a like super bright, nice star. Well, maybe not super bright, but a bright star, non-degenerate bright star there. Let's have a look. This is what Cristina and Mario have done by looking at archival HST data. In the blown up section there, the green dot, basically, well, there is a little error circle there. It's the position, the timing position of our pulsar. And as you can see, there's nothing within something like 6, 7 sigma. The closest stars are those two red and blue ones, which are, I think, respectively 6 and 8 sigmas away from the very precise location of our pulsar. So there is no optical counterpart, which means that the companion with a mass between 2.1 and 2.7 solar masses has to be a compact object. So the only options that we are left with is either this is a very massive neutron star. The most massive neutron star that we knew of till now had a mass of 2.08, I think, solar masses. So this is minimum mass 2.1, or, which would be probably even more intriguing, a low mass black hole. Which, I mean, having a low mass black hole with a pulsar with a precise clock orbiting around it would be super interesting to study the black holes very, very precisely. So this result has been published a month ago. You may have seen also the media INAF and press releases about it in Science. The title that we gave is a little long, but descriptive: a pulsar in a binary with a compact object in the mass gap between neutron stars and black holes. In fact, if we draw this little graphic with the constraint that we have on orbital inclination on the x-axis and companion mass on the y-axis, the red curve is the constraint that we have on our pulsar, and when we have when it's dashed, it's outside the limits that we have for the lack of detection of these extra relativistic parameters. We can see that its mass falls very, very well. It's very well within this mass gap in which we don't know what kind of stars, what kind of compact remnants might be created, either neutron star or black holes. As I was saying, the heaviest neutron star that we know of is a pulsar, is this pulsar J0740 that you can see in the right side of the plot in blue, which has an estimated mass of 2.1, more or less 2.08 solar masses. And the lightest black hole that we know of has a mass of something like 5 solar masses. If we go and look for gravitational wave products, though, we can see, as you can see again on the right-hand side, so the red is the mass range for our pulsar. The blue are the two most massive pulsars, masses of neutron stars from pulsar measurements. This in gray is the product of the merger of the two neutron stars from the gravitational wave, say 17, 18, 17. So the double neutron star merger, the very famous one, which is very well matching the mass range of our system. And in black, we have mass estimates for the lowest component mass of LIGO-Virgo mergers of either black hole or black hole neutron stars. And this one here, for instance, which again falls very well in the same range as our, was also indicated as a possible product of a previous merger. So this is one of the two components of a merger, but the authors that published the paper on this already thought that maybe, given the mastering, that might be the product of a previous merger between either two, between two neutron stars probably. So the idea that we got out of this is that our system has been formed by the encounter between a normal millisecond pulsar with had its white dwarf companion created through the normal channel with the neutron star with a low mass companion star that at some point accretes matter from the companion star in a low mass X-ray binary and then gets a millisecond pulsar plus white dwarf in a circular orbit, encountering with a binary single exchange encounter, either a single black hole or a single neutron star that comes from a previous double neutron star merger. So this is the idea. After the encounter, we will have our system with very high eccentricity because of the exchange encounter and a runaway white dwarf. So either way, whatever our companion star ends up to be, it's very exciting. If it's the most massive neutron star we know of, it has very interesting implication on the neutron star equation of state. It's very, very heavy, so it excludes many possible proposed equations of state for neutron star. And if it's a black hole, we have, as I was mentioning, a clock orbiting around black hole. And so we may have, by keep on following up this system, very interesting information about black holes themselves, their spins, their masses, etc., etc. So I think I am out of time, so I will skip on those further results. As you can see, I listed many, many different other results from the other different subtopics that I didn't have the time to touch upon. But all in all, we discovered 150 pulsars in less than 4 years, doubling the pulsars in the globular clusters, increasing by a quarter the pulsars in Fermi, etc., doubling the number of pulsars known, for instance, in the Small Magellanic Cloud. We published something like 50 papers on many, many different topics. And the future is even brighter because now we are using MeerKAT with 64 dishes, which already is 4 times as sensitive as Sparks and twice as sensitive as the GPT. But soon MeerKAT will have an addition of further dishes. It will have 80 dishes in the MeerKAT Plus and even further bandwidth that we can use to study pulsars. Well, and not only, of course. And of course, the final aim is to exploit the full SKA1 meat, which will have 197 dishes. And thanks to these improvements in sensitivity and search speed, we will end up discovering hopefully something like 3-4 times as many pulsars as we know of now, including a very large amount of millisecond pulsars, which are the ones with which we can do many, many of these fine experiments. And in particular, we will have something like 100 or 200 relativistic binary pulsars to do all these extra studies with, among which hopefully some other interesting systems as the last one that I showed you just before. So stay tuned for the SKA and even for the remaining of the pulsar experiments with MeerKAT. I continue.